Okay, here we go. Part 3, using velocity graphs to get more information and to help us develop the kinematics or motion formulas that we're going to be using quite a lot. So in the previous 2 videos, we discussed how we could get from a position graph, we could then get velocity information. Then we could use that velocity information in order to actually get back to position information in the form of displacement. And that led to a big idea that the area trapped between a velocity graph and the time axis, as I said here, the bounded area, gave us displacement. And we proved that to be within the bounds of what we could do to be universal, because we did it with a constant velocity and found the rectangular area, produced the displacement we knew we were supposed to get, and then we did it with a decreasing velocity that formed a triangular area. Well, it works for everything. So we're going to use that idea and expand on it a bit more in order to develop the rest of the kinematics formulas. But I figured we should just go ahead and take a look at them all at once quickly to make sure that we can write it all down and know what we're talking about. So up here in constant velocity or uniform motion, where something is not speeding up or slowing down, we have a pretty simple equation. And this is the equation of motion for a position time graph with a constant velocity. So here v bar represents the average velocity, t represents the independent variable, x0 or x0 represents the position at time 0, also known as the y-intercept, and that's our equation. So pretty straightforward. We already did that. I just wrote it in slightly different order because typically you start with a constant and then you work your way up in the variables in most physics texts anyways. Then we get on to accelerated motion. And I don't want to spend forever on this, but doing the same process we did to find the position equation from a position graph with constant velocity, we can use a velocity graph and write an equation of basically a slope-intercept form equation for it. And that'll give us the new velocity of an object at some particular moment in time is going to be the original velocity, v sub 0, plus the acceleration rate multiplied by time, where the acceleration rate is going to be the slope of a velocity graph. Now, you notice there's no bars over these velocities because they're not average velocities, they're instantaneous. They're at an explicit moment in time. What velocity are you going? Not over some giant time interval, but at an exact moment in time. So there's no bar on those. You're not going to see bars on any of these. Technically, we could put a bar over the A, but typically we don't, just because it tends to get a little cluttered. And in fact, for the constant velocity equation, sometimes we don't put a bar over that. We'll put a subscript of x to represent it's the velocity in the x direction. So anyways, this equation we can get from a graph of velocity versus time. This equation right here, we're going to show also can come from a velocity versus time graph using the idea of area. And these other 2 equations, these beasts right here, they're going to come from substitution and solving for, solving out a variable, essentially. This one right here is extremely common. You're going to use it quite a lot. The 4th one gets used a fair amount, sometimes called the Tricky Ricky equation, just because it's hard to remember and sometimes people don't know when to use it. It's not too bad. Anyways, let's go ahead and draw like just a made-up velocity versus time graph here. And I'm going to make it so that it's not starting at 0 velocity. Let's go ahead and give it some initial value here. And then over some time period, it's going to go up. And, it really doesn't matter to me where it goes. So I'm just going to draw a line up like that. Except I didn't want a line like that. I wanted, there we go. Let's just say there. So I've got a velocity versus time graph. And I realize now that I made that way too big. So let me go and shrink that down a bit, like to there. Move that dot over. Oh, wonders of technology. So here's my velocity versus time graph. Now this velocity is increasing. It did not start at 0. And as time goes by, it steadily increases to a new velocity. And we could write an equation for this line using slope being the acceleration, initial value v0. I'll write that down here. That's our velocity at time equals 0. And then at some point in the future, we have a velocity v, whatever that happens to be. And that happens at a particular moment in time, t. So if we knew that the slope here would be represented as rise over run, some delta v over delta t, that's equal to the acceleration. So that's where the equation up above, v is equal to v0 plus at, comes in. Time is still the independent variable, so it's there, it's multiplied by the slope, and then the y-intercept, or the vertical axis intercept, is v naught, or v sub 0. So that's where this equation can come from. So let's put a little check mark next to that we've sort of proven that. We didn't go in too much depth, but it's there. The second equation is going to come from the displacement. So here, delta x represents displacement, not a specific position, but how much you've changed position. And we said that the area trapped between a velocity graph and the time axis, this area right here, would represent the displacement. So let's go ahead and prove that we can get this equation right here from this graph. And if we're going to look at it in terms of area, you should recognize that this shape is a trapezoid that's kind of fallen onto its side. Fell down, go boom. Where the two parallel sides are not on the top and the bottom, they're on the left and the right. So if we take the idea that area represents displacement, but here we recognize that it's a trapezoid, where we would have 1/2 the height of the trapezoid times base 1 plus base 2. We need to label, sorry, I was covering up my words there, we need to label what these sort of fundamental trapezoidal dimensions are on our graph. So the height is always the distance between the two parallel sides. So in this case, it's going to be my time axis. This represents the height of my trapezoid. Even though it's fallen over, it's still, if you're 6 foot tall and you're laying down on the ground, you're still 6 foot tall. Technically, that's your height. Then we've got our two bases. And we can say that the first base, base 1, is right there, and the second base is right there. And if we go ahead and translate that into what's on our graph, the height is the time t that's gone by from 0, and the base 1 and the base 2 are our original velocity and our new velocity at time t. So if we translate this into graph speak, we would have 1/2 multiplied by the time that we're looking at, the base 1 plus base 2, which up in the equation up above, you can see that I swapped the order, but additive property of equality, or whatever you call it, commutative property of equality for addition. It doesn't matter what order you add them. So I can put v plus v0, and because that is the area, it should represent the displacement. So the displacement from time 0 to time t, wherever time t is, will be given from this formula. Let's put a little check next to that. Now, you might be thinking, but no, that doesn't look at all like what we did up above. Well, let's say that the original velocity is 0. If the original velocity is 0, we would have 1/2 time and then final velocity, and it would look more like a triangle, which is what we did before. So this equation is universal. You can have it if the original velocity is equal to 0, if it's not equal to 0, and then if the original velocity and the final velocity are the same, you just get 2 times v here, multiplied by 1/2, so the 2 and the 1/2 would cancel, and you just have average velocity multiplied by time, which is what we had in a previous video. So this equation, cha-ching, it works. Now, we can't get anything else out of this graph. But what's really, really important here is that both of these required, sorry, my D didn't work out there. There we go. That's too hard to read. I'll switch to blue. The D required us to have a constant, not changing, but a constant acceleration. I can't find the area of a trapezoid here if it's not a trapezoid. If this is a curve, because the rate of change of velocity is not constant, well, this doesn't work. This equation only works if it's trapezoid. Up here, the equation for velocity can only follow a slope-intercept form if the acceleration is constant. It has to be linear. So all these equations are going to be based off of constant acceleration. The acceleration does not change with time. Now, how do we get to the other two? Well, we get to the other two by substitution. In a nutshell, it's not necessarily pretty. It can be a little kind of messy. I'll kind of show what you can do for it, but I would like to start by saying that this equation shouldn't be a surprise. The one with the 1/2 at squared. This is a quadratic formula that says position is determined by a squared relationship with time. That's parabolic. Now, if we go back to what we did with the old battery rolling down the incline, let me go ahead and get rid of the velocity graph because it's taking up space. This is a parabola. It's only half of the parabola. We've got the left half of it, but it's parabolic. The position of an object that's accelerating, if the acceleration is constant, and we knew it was constant because when we did the velocity graph, it had a constant slope. Constant acceleration, you get a quadratic equation like this. And we modeled it off of a quadratic equation. We've got an a value here, which for kinematics formula will represent 1/2 the acceleration. We've got a b value here, which according to our equation will be the original velocity. And we already know that is because we did it in a previous video. And then we've got an initial position for the c value, which is 0.002, which is, well, that's really small. That's like 2 millimeters. So this is a quadratic relationship. This is what we saw, and the kinematics formula bears that out. So how do you get to it? Let's take a look. So one thing that we need to, before we actually do any substitution here, we need to kind of make note that the x, the delta x there represents a change in position, so that would be final position minus initial position. And we do not have that technically down below in this equation. We wrote it with the x and the x naught, the original position, separate. We can rewrite this as delta x equals v0t plus 1/2 at squared. In that case, we're just subtracting the the x0 to the other side, which becomes a delta x then. X minus x0 is delta x. But anyways, let's go ahead and take these two equations and substitute them into each other. We'll do the setup. I'm not going to go through all the algebra because it's really time consuming, but in this equation down below, we've got starting and final position, or delta x. We got starting velocity, time, acceleration, time. There's no final velocity here. So we've got this formula that is set up as final velocity is equal to original plus at. If we substitute this expression into the final velocity below, we can then do a bunch of algebra and simplify it. I'll go do that setup here. We can take delta x is equal to 1/2 t, and then where the v would normally go, we'll put v0 plus at plus v0, and then you would go ahead and simplify this. I'll do the first step here. You do 1/2 t. You have a v0 and a v0, so that'd be 2v0 plus at. And then if you were to, distribute the 1/2, the 1/2 and the 2 would cancel, but then you get the 1/2 on the at, and then that would square it, and you get the t there. If you distribute it, you get the equation up above, right here. And if you wanted to instead get rid of the time, which if you look in this last equation, the v squared, there's no time in this equation. There's only position, accelerations, and velocities. You would take this upper equation, solve it for time, and then substitute in it for the t down below, and then you do a whole bunch of algebra, which I don't want to do. So anyways, we're going to leave it there with these are the equations. And we'll note that you can't jump back and forth between these. If you're using the constant velocity equation because something's moving at constant velocity, you cannot jump in here to use one of these others. And so same thing, if you have an accelerated equation like the battery rolling up or down the ramp, you can't use the constant velocity equation. You're in one or the other. So we'll go ahead and leave you with a table of variables that you can use and reference and copy down. All right, and here's that table. We can fill this in with way more stuff as the time goes on, but we've got X represents the position measured in meters, T represents time measured in seconds, V represents velocity or speed, meters per second, A represents acceleration in meters per second squared. Over here on the side, I got some generic variable Z, which is not used for anything. Um, so if it has a 0 as a subscript, that means original or at time 0 seconds. If it has a bar over the top of it, just a bar, that means average value of Z. And if it has a delta symbol in front of it, that means change in Z, which means a final value minus an initial. We'll also have vector symbology soon, and we'll have other versions of these sorts of things right here. But that kind of wraps it up for now. I'll see you again later.